Hi, welcome back. My name is Himanshu and this is 12th lecture in this course on Bayesian modeling. The topic for today's lecture is likelihood function. But before going into what exactly a likelihood function is, I just want to wrap up what we started in the previous lecture. That is how to use the probability distributions in R. Okay, so we already know about probability distributions. So we are going to see how to use these probability distributions in R. So primarily how to generate random values of your random variable, right? So how to generate values of your random variable from a probability distribution. And you can also do other things like how to calculate area under the curve in R, area under any probability density function, right? So we'll see how to do all those operations. Okay, because this is a very important skill that you need to learn in order to work with these Bayesian models in R. Okay, if you are not comfortable with R, you can do all these things in Python as well. It would be very easy to do all this in Python as well. Okay, so you just need to figure out what is the right function to generate random values from a distribution, right? So for example, we were talking about binomial distribution in R in the previous lecture, and we saw that the function that we use to generate random values from a binomial distribution is R binom. Okay, so for example, here I'm generating a single random value from a binomial distribution with sample size 50 and underlying probability of success being 0.9. So you can think of it as you are tossing a coin 50 times where the probability of heads is 0.9. Or let's say you are doing a word recognition task where you are given 50 words one by one, and the task of the participants is to recognize them. Okay, and this is the probability of a correct response, let's say 0.9. Okay, but here I'm just simulating a single experiment. So n is equal to 1. That means in a single experiment, how many correct responses would be there out of total 50 trials? Okay, so let's see. So we run this line of code, and when you run xsim, so xsim comes out to be 47. So that's the output. Okay, so that's one value of the random variable that we have generated from a binomial distribution, right? What will happen if you run it again? You will get a different value, right? Because it's a generative process, so it will generate different values depending on the underlying probability mass function. What is the underlying probability mass function? Well, it's a binomial distribution with underlying probability of success being 0.9. So highest probability mass would be somewhere around 45. At 44, you will have slightly lower probability mass. At 46, you will have slightly lower probability mass, and it will keep on decreasing on both sides of the 45, right? And you might have zero probability mass beyond, let's say, 30 for values less than 30, right? So that's how it works. And that's how it will give us values, right? So it will give you, mostly it will give you values between, let's say, 35 and 50, right? Here I'm I'm not simulating these experiments one by one, but I'm simulating 10,000 experiments in a single line of code, right? So I'm simulating 10,000 experiments, assuming that each output, the number of correct response in each experiment, has a binomial distribution with sample size 50, underlying probability of success 0.5, and let's see what happens. Well, let's say 0.9. Okay, so let's see what happens. When I simulate this, I get 10,000 values in basically in each experiment, and when I draw a histogram of all these values, I get a histogram like this. So what this histogram shows us is that most likely, so the highest probability mass is actually at 45, okay, but even at 46 you have some probability mass, almost similar probability mass but slightly lower. At 44 and at 47 you would have lower probability mass, right, and it keeps on decreasing. Beyond 36 you do not see any data points here. So even when you are generating 10,000 experiments, you do not get an experiment where you observe less than 36 number of successes, right? So that's how a binomial distribution works, right? So if this is indeed the true generative process, right, if this is the indeed true generative process behind an experiment, and if you repeat this experiment 10,000 times, then this is how the data would look like. Okay, the data you are seeing in this graph, in the histogram, right? Let us see how do we draw the graph of the probability mass function. So let's say underlying probability of success is 0.9, and we want to draw a graph between, let's say, 20 and 50, or maybe you can take values from 1 as well, okay, or maybe 0. 0 is also possible. So these are all the possible values of the random variable x, right? Let us generate this. This is what you see. See in this graph, for values less than around 38, okay, all these values of the random variable have probability approximately near 0, but the values greater than 35 have some probability, right? And the highest probability mass is here, then slightly lower here, here, right? And keeps on decreasing on both sides, right? So you get a graph like this. Now this is a discrete graph, by the way, right? This is not continuous because you do not have any probability between, let's say, 44 and 45, right? Probability between 44 and 45 is unknown here. Basically, you can say 0, right? But there is some probability at 44 and 45, right? It's a probability mass function. So that's how you would draw the graph. Never join these dots together, okay? All right. So this was for a binomial distribution, right? By the way, the function I have used here to draw the graph of probability mass function is d binom function, right? So this function is different from r binom. Using r binom, you generate random values from binomial distribution. Using d binom, you calculate probability mass or probability density of a given value of random variable. Okay, so that's the difference. So let us do all these operations for, let's say, a normal distribution. Okay, so let us say you have some reading time data, okay, such that reading time in ith trial is assumed to come from a normal distribution with mean 300 and standard deviation of 50. Okay. Now let us see. Let's say this is the underlying generative process, that mean 300 and standard deviation 50. So let us generate reading time in 1000 trials from this underlying generative process. Okay. So let me call it sim RT. So simulated reading times or reaction times, whatever. It's a human experiment. So you are recording, let's say, reaction time, okay, or reading time, doesn't matter. So the function that you use to generate from a normal distribution is R norm. Okay. What happens is that in R norm function, you will first thing that you would give is number of data points that you want or number of observations that you want. So let's say you want 1000 trials, okay, 1000 observations, okay, in this experiment, and then you give the mean. So what is the mean parameter? Okay, so mean parameter here is 300 and SD is 50. Okay, so this would give us 1000 observations of simulated reaction time from this particular distribution. What is the distribution? Normal distribution with mean 300, sigma 50. Okay, this is how the values would look like. Remember, this is a continuous distribution now, so that's why you see these fraction values, right? 387.7337, right? So you don't see integer values anymore. Now let us draw a histogram of simulated RT and let's see how it looks like. This is how the histogram looks like. See, this is histogram of simulated reaction time from normal 350, right? 300 is the mean, ST is 50. What you would see is that the mean value is around 300. So 300, you can see here, it's the mean of this distribution, and it would be approximately 300 because just a sample from this distribution, right? And most of the values would lie between, what would be the 95% interval for a normal distribution? 300 minus 2 into 50, approximately 2, 300 plus 2 into 50, right? So 300 minus 2 into 50 is 200. 300 plus 2 into 50 is 400. So most of the values will lie between 200 and 400, and that's what happens here, right? So this is 200 and here is 400. So most of the values lie between 200 and 400. Right? So this is how a normal distribution looks like if you draw random values from a normal distribution. This would look much more smooth if you, let's say, draw 10,000 values, okay, rather than 1000. Now you can see a proper normal distribution, right? Centered around 300, and you can see the symmetry. It's totally symmetric around 300, and that's what happens in a normal distribution. And most of the values are between 200 and 400. Okay? All right. By the way, if you calculate actual mean, right, actual mean value of these data, this won't be exactly 300, right? It comes out to be 299.82, right? Why? Can you tell me why it is not exactly 300? Because you are drawing a random sample from this generative process, right? So what happens when you draw a random sample? Well, you randomly are drawing 10,000 values from a normal distribution with mean 300, ST 50, right? These 10,000 values could be different when you, let's say, you draw these 10,000 values again, right? You again draw 10,000 values from the same distribution, okay? This would be slightly different from the previous one. See, now the mean is 300.10. This is exactly because the values we are drawing are random values from normal distribution. So they would have some randomness. There would always be some randomness, right? And that's why you won't get exactly the same mean, right? That's impossible. Similarly, ST won't also be exactly 50, right? So in this case, it's 50.11. All right. So this is how you can generate from a normal distribution. Now, how do I calculate probability density of a particular value of random variable? So let's say value of the random variable is let's say 400. Okay, so let's say value of, let's say, some RT, some reaction time is 400. So that's this is what you have observed in an experiment, and you want to calculate what is the probability density of observing this value, given that you have a normal distribution, okay, with mean 300 and ST 50. So you can use d norm function. Okay, so d stands for density. So this is the function that calculates probability density of a particular value of random variable being generated from a normal distribution, right? So x is RT, or you can just write 400. So for this value, you want to calculate this probability density, and mean of the distribution is 300, ST is 50. So this would give us probability density for 400, and this is what the value is, 0.00107, right? Similarly, let's say you want to calculate it for 300, it would come out like this, and slightly higher than 400 because 300 is closer to the mean. That's why this probability density is higher. You can also calculate these probability densities for multiple values. So let's say you want to calculate it for multiple values. Let's say 200, 300, 400, 500, right? You can calculate for all these values in a single line of code, right? So I'm getting these probability density values for all these, sorry, there's dot. So there are 4 probability density values corresponding to each value of RT, right? I can use this to draw the graph of probability density function as well, right? How? So let's say I create a vector of RTs, let's say from using sequence function, I can generate it from, let's say, 100 to 500, and how many data points I want between 100 and 500, let's say 10,000. Okay, so it will equally break this real line between 100 and 500 into 10,000 points, and for each point I can calculate probability density using d norm function. Okay, so here I will pass on RT, mean is 300, ST is 50, right? So I have calculated RT as well as density. Now if I plot RT versus density, I will get a graph of probability density function of a normal distribution. You can see that the highest point is at 300, and this is the mean and median as well, and there is a symmetry around this mean, right? And the ST is 50. So this is the graph of the probability density function, the normal distribution, right? All right. So in the same way, you can basically use other distributions in R as well. For example, Poisson distribution, beta distribution, right? You can also do a couple more things. So for example, let's say this is the probability density function, right? And you want to calculate area under the curve between 300 and 400. So let's say between this point and this point. How would you calculate area under the curve, right? So there is a function called P norm. P stands for probability. Okay, so norm stands for normal distribution. So what this function does, it calculates probability of observing a value between minus infinity and to a particular value of x. So let's say if I ask it to generate how much is the probability mass between minus infinity and 300. So basically what is the area under the curve from minus infinity to 300. Okay, so I can use P norm function. So I will give 300 here, mean is 300, ST is 50. Okay, do you know what would be this probability between minus infinity and 300? This is a normal distribution. It should be 0.5, right? Because this is exactly half area between minus infinity and 300. 300 is the mean value. See, so you see 0.5. So let's say you want area under the curve between 300 and 400. This thing is giving me area under the curve from minus infinity to 300. Okay, and this thing would give me area under the curve between minus infinity and 400, so which is 0.9772 something, right? If I subtract area under the curve from minus infinity to 300 from area under the curve from minus infinity to 400, so what I would be left with would be area under the curve between 300 and 400, right? So this is exactly comes out to be 0.4772. Right, so this is how I can calculate area under the curve between 2 points. Okay, you can also calculate quartile. So basically, range of a particular probability interval. So using a function called Q norm, right? So let's say I want to calculate between which two values I have 95% probability mass. Okay, so for that, what I can do is this. Let's say I will leave 2.5% probability mass on the left hand side, 2.5% probability mass on the right hand side. So the probability mass in this region would be basically 95% in the central region, right? So how do I do that? I can do it like this. I would write the quartiles here. So I want probability mass between 0.025 and 0.975. So basically this 95% region, middle region, right? From a normal distribution with mean 300 and ST 50. Okay, so this gives me 202.0018, 397.9982. Right? This is exactly the 95% region, basically the region which contains 95% probability mass in a normal distribution with mean 300 and ST 50. Okay, so this is the exact value. We calculated approximate value which was between 200 and 400. This is the exact value. All right, so this is it from probability distributions in R. Okay, now this would be very useful in calculating likelihood function and further on in working with Bayes theorem, right? So we'll come back to this later. For now, we will start what exactly is a likelihood function. So you already know about probability density function. So let's say you have a continuous random variable x. So x is a continuous random variable. and the underlying probability density function, okay, for this random variable x is f of x theta. So, this is the underlying probability density function. By the way, you can write statements like this, right? See here, I am using this wave sign, simulation sign. This is called a simulation sign. What I am saying is that x is being drawn, x is a random variable, right? So, values of this random variable are drawn from this generative process f of x theta, right? Because this probability density function is our assumption about the generative process. So, what we are saying is that values of this random variable x are being drawn from this generative process. The values of this random variable comes from this generative process f of x theta, right, where f of x theta is the probability density function of this random variable. Okay. So, this was your continuous random variable and this is probability density function. Okay. Can you draw the graph of the probability density function? How would you draw the graph of a probability density function? You just drew it for normal distribution in R, right? But importantly, in order to draw the graph of the probability density function, right, the things that you need to remember is that graph of PDF means that random variable x is on the x-axis, right. So, we are going to draw what is the probability density of each value of the random variable of each value of x, right. That is what we want to draw, right. So, something like this. So, we want to draw a graph like this, but this function, the probability density function, is a function of two arguments. It takes x as well as theta. It has two arguments, x and theta. Then how you can draw a graph only with respect to x? Okay, it is not possible unless you take some fixed value of theta. So, let us say you assume theta equals to let us say some value 0.7, I do not know, it would depend on what the PDF is, right. Once you assume a fixed value of theta, only then you can draw the graph of PDF. So, basically graph of the probability density function is the graph between values of the random variable and corresponding probability densities under some assumed fixed value of theta. So, when theta is known, okay, you call it known and fixed. Okay. So, when theta is known and fixed, you can draw the graph of the PDF, right. So, for different values of x, you can calculate what would be the probability density because theta is known, right. Remember, when we were drawing graph for PDF for normal distribution, we were assuming that mu was known and ST was known. Only then you could draw the graph of PDF of normal distribution, right. Otherwise, you can't draw. Okay. So, this is called the graph of probability density function. Now, this is something you can draw before even seeing any data. Okay. What do I mean by that? So, let us say you do an experiment, you plan to do an experiment, okay, plan to do an experiment, okay, where your random variable is x. So, basically the outcomes you are going to observe in this experiment is exactly this random variable x, right. So, values of this random variable, okay, and you have already assumed that x, the outcome in your experiment, would come from f of x theta. So, this is your assumption about the outcome of the experiment, right. Once you have made the assumption, then you can draw or visualize what kind of data you might expect in this experiment. So, you can draw a probability density function with respect to values of x, assuming some fixed value of theta. And if you are not sure about what would be theta, you can draw these graphs for different values of theta as well, right. But this is just for visualization, that what kind of values you might expect in this experiment for a given value of theta, right. So, this is something you are doing before seeing any actual data, right. So, this is the graph of your assumptions, okay. So, the graph of PDF can also be called the graph of your assumptions, right. And what are the assumptions? In this case, you are assuming that x comes from f of x theta and theta equals to 0.7. So, you are drawing this graph under these assumptions. Okay. Now, now what would happen once you have some data, right? So, let's say you did this experiment and you collected some data, basically value of random variable, and the data is like this. You observe that the value of x observed in the experiment is actually, let's say, 40. So, this is observed data now. Okay. So, this is data. This is your observation. Now, once you have data, right, think about this function, probability density function. Once you have data, then this quantity, this particular argument of this function becomes fixed and known. Okay. Now, x is fixed and known, right. So, it does not make sense to draw a graph with respect to different values of x, because x is fixed and known now. What you can do instead is draw a graph of this probability density function. It is the same function f of x theta, right, with respect to different values of theta. Okay. Given that x is fixed at 40, x is known and fixed at 40. Okay. This time the graph you are drawing is with respect to theta. Okay. So, let us say here is 0.7, here is 0.5, here is 0.8, here is 0.9, right, something like this. So, this is a graph of this probability density function with respect to theta. What is happening here is this, that this graph is telling you that if you assume that x, the outcome in your experiment, comes from f of x theta, and you observe in your experiment that x equals to 40, right, then these values of theta are likely to generate this data x equals to 40, right. So, under the assumption that outcome in your experiment comes from f of x theta, these values of theta are likely to generate the observed data x equals to 40, right. Which values of theta? So, you will see that some values of theta have higher density, some values of theta have lower density. Interpretation is this, that these values of theta, so let us say this value of theta is more likely to generate the data x equals to 40 compared to this value of theta. So, this value of theta is less likely, let us say 0.75 is less likely to generate x equals to 40, 0.7 is more likely to generate x equals to 40, and let us say something like 0.9 is almost unlikely to generate this data, right. So, what this graph is telling you is that which values of theta are more likely to generate the data x under the assumption that x comes from f of x theta. Okay. So, which values of theta are more likely to generate the data and which values of theta are less likely to generate the data, right. So, in this case you can say 0.7 is most likely to generate this data. Values around 0.75, 0.65 they are less likely to generate this data. Values around 0.9 are almost unlikely to generate this data, right. This graph is called a graph of the likelihood function. Okay. So, this function f of x theta with respect to theta, this function is called the likelihood function. Okay. This is called the likelihood function. Okay. And you can say the difference. So, the probability density function is a function with respect to your random variable x when theta is known and fixed, right. This was your PDF, and likelihood function is a graph of your f of x theta with respect to theta when x is known and fixed, when data is known and fixed, right. So, that is the basic intro of likelihood function. So, the idea is this, that for a given random variable, let us say x, right, you assume that this random variable has a probability density function f of, let's say, x theta, right? If you draw the graph between different values of the random variable and the probability densities, corresponding probability densities, assuming some fixed value of your parameter theta, then that graph is a graph of probability density function. Okay. But if you draw the graph between theta and probability densities, assuming some fixed value of your random variable, some fixed values of your random variable, then that graph is a graph of a likelihood function, right? So, because your probability density function f of x theta is actually a function of two arguments, random variable x, value of the random variable, and parameter. So, when parameter is fixed and known, then the graph you draw with respect to x is called probability density function, and when data is known and fixed, then the graph you draw with respect to theta is called the likelihood function. Okay. So, we will come back to the likelihood function in the next lecture. Thank you.